Good morning, everyone. First, I would like to thank the organizer for the invitation. Also, I would like to say that unfortunately I was not able to make my video working. But I am very happy to be with you today, as you can see onto the picture that I take. I would like to motivate my talk by rapidly speaking about non-emission photonics, which is receiving quite significant amount of attention nowadays. And probably the reason is that the physics which is associated, and therefore the possibilities also associated to non-emission photonics in comparison to emission photonics are much more broader. And so there is a lot of activity nowadays into this field. So another reason why people are quite interested into this non-emission photonics is due to the fact that basically the most important element, which is a nanoresonator, is evolving very rapidly over the 20 past years, and you have many applications of this element. Here I just try to summarize what have been starting from the whispering gathering mode of sphere or microsphere and going to microcavities with very high Q factor. And then later on, I mean, there have been these plasmonic issues, which nano gap cavities very recently, where you have a Q factor which is much smaller than in this case, but the mode volume at the same time has been reduced drastically to maybe the ultimate confinement, which has been reported by the group of Jeremy Bumber in 2016 with the so-called pico cavity, where basically the confinement, the mode volume, is something which is very similar to the size of one molecule. I would like to first recall the difference between an Hermitian and a non-Hermitian system, and this can find this difference in maybe any textbook on quantum mechanics. But here I just refer for the Hermitian physics to the case of this photonic crystal book, where basically I found it a presentation which is very well made for Maxwell equation. I just recall that in that case you are dealing with closed conservative system, where the operator is self-adjoint. The eigenvalue are real, and the eigenmode, which are called normal mode, also form a complete set. They are orthogonal and they can be normalized in a very classical way. In fact, in all, I would say basically all our photonic system, the system is open, so it's a dissipative system, and in addition you can have absorption. And then none of the nice property that I have reviewed rapidly for the Hermitian case still hold. And especially what is very important is that the eigenvector are now, the eigenvalue are now complex numbers. And the eigenvectors are also now called the quasi-normal mode. So the mathematics associated to this open system is more challenging, but there have been quite a significant amount of improvement which has been performed the last 10 years. And I would like to review this event that has been done recently. But first, before going to, I would say, important result in the field, I would like to maybe for the electromagnetic case focus again about the difference between the normal mode and the quasi-normal mode. And I'd like to say that for the normal mode, I mean, I take the Maxwell operator. Of course, as I define a mode, I remove any kind of source. So it's a source-free Maxwell equation that I am solving here. In the Hermitian case, omega is real, the quality factor is infinite. Epsilon should be real, there should not be any absorption, and then it's easy to see when you inject this into Maxwell equation that you can choose as a solution that E is going to be real and H is going to be purely imaginary. And then when you take the real part of this quantity to get the physical field, which is real always, then you get this kind of solution where basically you see that the E field or the H field can be decomposed as the product of a function which is depending on space multiplied by a function which is depending on time. And basically they are out of phase by pi over 2, which is due to the I term here. How to say that? We have a standing wave. And the best case for illustration is the case of a Fabry-Perot cavity with perfect mirrors. This is a spectrum that you observe. For this cavity, for instance, they are all on the real axis because the imaginary part of the eigenvalue of the frequency is real. If you go to the non-Hermitian case, then you have to solve the same Maxwell equation, but this is an open system, so you have to satisfy the outgoing wave condition. Right? It's no longer closed. And then, in this case, what you have is that basically omega become complex. I mean, in fact, the imaginary part of this omega is related to the quality factor or the mode lifetime. If I could say epsilon can be complex, of course, you can accommodate for absorption. And in that case, E and H are both complex quantities. And when you take again the real part, what appear here is a phase term here, which make that you cannot any longer write this eigenmode, which I will call the quasi-normal mode, as the product of the function which is depending on space multiplied by a function which is depending on time, which means you don't have any longer a standing wave. Even in that case, what you have is a progressive wave with propagation, if I could say, which is due to leakage. And of course, the eigenspectrum is no longer onto the real axis. Here I show the existence of this quasi-normal mode. They can be observed. Definitively, they can be observed. So they are very important to understand the physics of any non-Hermitian system. And here I take the case of acoustic wave here, which has been recorded at one point in space. And what you see is the evolution of the acoustic signal as a function of the time at this point. You have an initial strike of this Helmholtz regenerator. I take it from the web, right? Where you see you have a transient regime where probably you excite many quasi-normal mode with a lifetime which is extremely short. But after a while, what you can see really as a signature is probably the fundamental mode, quasi-normal mode of your system with a lifetime which is quite long, and you see a nice oscillating function with an exponential decay. Now, what I plot here is as a function of time. I just want to mention this point. Is as a function of time, you are exponentially damped, right? It means that for a fixed time, as a function of space, you are exponentially growing up. And that's very easy to realize, because if you go away from your resonator, right, basically you have a spherical wave, which is the leaky wave, which is going out from the resonator, if I could say. And in this leaky wave, you have a propagating wave, so that means it can be written exponential I omega t minus r over c. And the minus sign cannot be escaped, it's propagation. So that means that if you are damped in time, I mean, obviously, you are exponentially growing. And you can see many articles, even by experts in the field, which are writing that this exponential divergence is unphysical. It's not at all. It's a direct consequences of the fact that you are exponentially damped in time. And that's causality. So the causality implies that in space, your quasi-normal mode should diverge exponentially. And you have to play the game with that. You cannot avoid this. In fact, this exponential divergence in time has led to a strong issue in the literature, at least in the literature in electromagnetism, about the mode normalization, which is very important, which is just before mode, as important as mode orthogonality, if I could say. And a lot of work has been, a lot of very nice work have been made in the 90s by what I call in general the Hong Kong group, with something like 20 papers which has been published on quite simple geometry, but establishing the basis, for example, of perturbation theory of quasi-normal mode. And what they have done here, they have made an error. I would not say an error, they have made an approximation, because in one, in two, at least two of their papers, they mention that the normalization that they provide for those simple mode is approximate. But the fact is that when this, starting from 2010, so basically 10 years after, I mean, people have looked at more complicated geometries, 3D geometries on substrate, something very practical case. And some of the experts in the field have taken here this normalization, introducing a mistake into the normalization method that were established at that time. And I would say that this has led to a strong debate in the literature, which is often misleading. And when non-experts are reading this article, they find the debate and they can have the impression that nothing is really solved nowadays and that it is complicated to normalize a mode. This is not the case. I would like to say and to emphasize with you, especially if non-expert is listening my talk, that this normalization issue has been completely solved. And we have recently written an article here where we provide in section 4 a clarification, a net clarification of the mistake that has been made over time. And we show that the debate is not a meaningful debate because, in fact, the problem of the normalization is absolutely clear or net nowadays. Here, I just want to show that, emphasize that we have two completely different mathematical approach, okay, that give, one is based on the residue theorem and the other one on the concept of a regularized Hilbert space, if I could say, define exactly the same norm. And here you have a numerical proof here from some complicated geometry, I don't want to go in detail, where you have the error which has been calculated as a function of the size of the domain you consider for the calculation, which means that as you increase the size, you feel more and more the divergence of the field, okay, of the normalized field. And you see the error between the norm, the two norms, defined mathematically by two different approaches, which has been implemented, and the error is very, very small. So in this article, we find a proof and a discussion of all, a clarification of this norm issue. About the completeness. The completeness is a little bit more tricky. Always in the same article, by the way, you can find a clarification about the completeness. I would like just to know that, in fact, I would like to rapidly to show how, in what sense it's complete. It is complete in a regularized space. So that means that in general, you can write the sum of your response as the total field is equal to the incident field plus the scattered field, and that the scattered field can be expanded into a basis of quasi-normal mode, which is completed, I would like to show you that after, by numerical mode. And the full basis now is complete. And the strength of this approach here, of course, compared to other Maxwell equation solver, is that you can have a straightforward implementation, because what is very important is that the excitation coefficient of the quasi-normal mode or the numerical mode, it's up to you, is analytical. So that means that you can reconstruct with transparent formula that makes the physics easy to interpret. And in some cases, when only a few modes are sufficient for having a high accuracy, or is sufficient for you, I mean, you can have a superior numerical efficiency compared to other Maxwell solvers. Let me try to illustrate that. Here is the case of temporal domain, where you have this antenna, which is composed of 3 metallic nanowires, which is illuminated by a pulse in the optical frequency range. And what is calculated here with the FDTD is the temporal response everywhere in space, but what we plot is a temporal response in a point close to the in the near field, right? And what you can see in this temporal response here, that here you see the incident pulse, but you see essentially a beating. When you have performed the calculation with the FDTD, you don't know what is beating. You see a beating, you see the solution, you are happy with that, but you don't explain what's happened. With the quasi-normal mode expansion here, we have computed the fundamental modes, I mean the important mode in the visible spectral range. We found only 3, which are plotted here. And then analytically, you can have the excitation coefficient. It's now called, it was called before alpha because we were in the frequency domain. Now we are in the temporal domain, so we call it beta. And so you can write that the response is equal to the response of the mode 1 plus the response of the mode 2 plus the response of mode 3. You make the sum and you get something like that, which is very similar. At least all the physics, I would say, is represented, and you explain the beating. You can have, if you don't want a high accuracy, I will discuss the difference between these two curves. If you don't want a high accuracy, then basically it's really helpful to use this method, because in the FDTD, imagine that you change the pulse width, the polarization, or the direction of the incident light, or you want to put a source which is in the near field, for instance, then you have to reperform the entire computation. You don't save any addition or subtraction of the previous calculation. Whereas in this case, if the modes are already calculated, you know all the fundamental modes, then basically this beta coefficient are non-analytically. So you get a very straightforward solution. I mean, just like this, right? It's analytic. Let me go to a difference between the two. I mean, of course, with three modes, you cannot have a very accurate reconstruction. And here in that case, you see that there is a difference between the reconstruction with the modal expansion and with the exact FDTD. I would like to discuss a little bit more into detail here. What is the mistake which is made? In the initial time, at short time, I mean, of course, the mistake which is made is due to the modal expansion. We have other high order modes, high frequency mode, which are excited and which are not taken into account into the expansion. So the solution is false. You can see that the solution can have a mistake of something like, I don't know, something like 5 to 10 or 20%. I don't know, I have not done that. Then you have a mistake also, which was more surprising here at long time. I would say, well, basically here you excite basically only the few fundamental modes of our system. There are three. With our software, we use console to compute the mode. I mean, the modes are very well computed. And in fact, the dephasing that you observe here, which is quite important, it's almost pi here in that case, is due to a mistake of the FDTD. You have a numerical dispersion in the FDTD. It's very difficult to encode a metal with round shape with FDTD calculations. Let me go to another example, which is now something like a few years old, which is the case of a bow tie. Now we are in the frequency domain. Okay, and I would like to illustrate the completeness. I would like to illustrate the difference between the quasi-normal modes, which are physically sound, and the numerical modes that we have to introduce to be complete. And here what we calculate in that case, we use the weekend for that, we compute the spectrum. So you have the imaginary part, the real part, and what you see here is that when the imaginary part is small at the scale of the figure, of course, you see the quasi-normal mode basically which are there. And all the other modes, they are more or less, I would say, or more sometimes the numerical mode of your systems. So let me go to that. So what you can do here is you can compute the extinction cross-section. So first what we use a reference method, COMSOL, at each frequency, this is a blue point, we compute the response of the system and compute the extinction. And then you can say, okay, I will take one mode here, and I will say that the field, the reconstructed field is simply alpha 1 multiplied by this mode E1. And then you can compute the extinction cross-section, and you will get the red curve. If you take 4 modes here, you will get 4 peaks. And if you take 10 modes, still there are all 10 quasi-normal modes in that system. You get this answer, where basically all the physics, all the resonance is quite accurately, I mean, you have to go into detail, but it's quite accurately represented. Actually, the error here is 10 to the minus 2. This is average error onto the full spectrum. So the error is significant when, in fact, the cross-section is small here, as in this area or this area. And then you can say, I'm going to use all these other modes. Have a look to this video where you see now we get these modes here, and then these modes, we decrease, we keep on decreasing here the error. Moving from 10 to the minus 2 with 10 quasi-normal mode to something like 10 to the minus 3 with 70 total modes. So you see, this is a penalty here, and this is where we are in the field. We don't know how to accelerate that. What would be the tool that we should develop or to accelerate the convergence, but the convergence is quite small. Recently, we proposed it's very simple work. I mean, a hybrid method to compensate for that. I mean, to mitigate the issue of having to take into account numerical modes which are slowly converging to increase the efficiency. So the general idea, I think, is very simple, and you get it from the previous slide, basically. You can say that the quasi-normal mode response is going to take into account all the peaks, all the non-smooth behavior of your response. I would say Fano response, for instance, can be taken into account with a quasi-normal mode expansion. But that, on top of that, you have to superimpose a smooth background. By smooth, I mean something which is varying slowly, gently with the wavelengths. And so what we propose to do is to predict this sharp variation with pole, with quasi-normal mode expansion, and to predict this smooth background with real frequency simulation by computing a few points at a few real frequency response right? And by interpolating. Let me show you into more specific case. In the case of where we have here a boat, we have here a patch, some kind like a patch antenna to simplify the description, where you see we have considered only 6 quasi-normal mode into our quasi-normal mode expansion. And the response is analytical, and this is a blue curve here for the field at some position in space, which is quite a short variation, as you can see, as a function of the frequency or the wavelength, in fact, here. And then on top of that, we compute the response of the system at something like 8 different frequency in the spectral range. We can build up, of course, a difference that gives us these 8 points here. And this difference, as I said before, if we have all the quasi-normal modes, should be a smooth function that we can interpolate, and the interpolation is the violet curve, if I could say here. Then you can make a sum between the blue curve, which is the quasi-normal mode reconstruction, plus the interpolated data here, and you get this curve, which is actually very, very accurate. So to compute that, we need only to compute 6 quasi-normal mode, and we need to compute something like 8 frequency domain response. And we have all the spectrum which is generated, and we have also all the physics which is provided because we have the quasi-normal mode, we have the analyticity of the expansion coefficient. We have also recently launched a software to do that. In fact, this software, which is called Modal Analysis of Nanoresonator, is a combination of 2 earlier softwares that we launched in 2013 and in 2018. I would say that with this software, you can basically solve any material. I don't like the word any, okay? But I mean many different materials, including dielectric, metal, anisotropic material, non-reciprocal material. We have also a toolbox for that. And you can solve, I would say, virtually any geometry because we back this software to COMSOL, which is using finite element and that can handle any complicated geometry with high accuracy. An overview of the software, if I could say here, of course, we have a tutorial, which is that we expect to be pedagogic and easy for the user to use. I would like to say that as a solver, we have in fact 2 solvers. We have the solver pole that can be used with any Maxwell equation solver. We need the Maxwell equation solver, but to compute the quasi-normal mode and to normalize them, we have this additional software which can be used with any frequency domain method. And then we have this egg solver, which is dedicated, if I could say, to COMSOL. Then we have a number of toolbox. Maybe the new one, which is very important, is a quasi-normal mode reconstruction toolbox. You have seen a few reconstruction before. We have also a non-linear toolbox. We have a grating toolbox. We have something like 10 toolbox nowadays. And associated to all this work and COMSOL model here, we provide a series of COMSOL model of various type. So that means that for the user, he can pick up the one which is the closest to the geometry you want to study, and then he can just modify the parameter, geometrical parameter, material parameter, and then can solve the problem. Now, let's say, I would like to conclude my talk by first acknowledging the participation of 2 postdocs that have worked in my group in Bordeaux, Wei Yan, which is now at West Lake University in China, and Tong Wu, which is still with me and is going to look for a position in the near future. And then I would like to say that the quasi-normal mode theory, in electromagnetism at least, is quite mature nowadays. I would say now all the fundamentals have been solved. Completeness, normalization, orthogonality, all that is well known. So what we enter a phase where we are in the refinement to make the theory more accurate from the point of view of the numeric, to improve, for instance, the convergence. That will be very, very helpful for the future. And finally, I would like to recall a few important papers written by my group over the past year, in fact more recently, if I could say, but anyhow. This is a first review article on the topic. Okay, well, it's quite complete review where you can find applications, fundamentals, numerical issues. Then we from this review, we made two recent smaller review, if I could say, more focusing. This one is focusing on the physics. We really well explain, I believe, and the difference between a normal mode and a quasi-normal mode. We also very well explain the two main physical parameters of a resonator, which are the quality factor and the mode volume. We explain the significance also of the complex mode volume and interpret it, why it should be complex. We have also this more, I would say, numerical oriented paper, theory numerical, where we go back into the normalization, orthogonality. We try to clarify some debate in the literature, and I think that's an important paper, which is really clarifying for a long time, I expect, and just mention our recent archive paper on the software that we have launched. With that, I would like to thank you for your attention.